And there's also, if you read the section, like some more slope field examples, it kind of ties them together a little bit better than we did yesterday. So, all right, let's just talk. So 6-1. I'm going to kind of have a lot of writing today, so I want to do it in here. I'm just going to write this all out. I should have just made you guys a copy.
You could.
You
still could go make copies.
Oh, the copy machines.
Oh.
I hear it's interesting.
There's no solution.
There's a copier in Miss Mansfield's office.
Like a small.
I used it yesterday. I'll do it.
Let's just write it down. It's going to be confusing because it's 2 pages. It'll be better to just write it down. So, we just have a lot of writing today. So when I could leave it out, but I think that you need some of the language here. So when you begin with a, what do you think that means?
Differential.
That means differential equation. I'm writing it abbreviated that way because that's the way you'd see it abbreviated a lot of the time. If you take higher level math, differential equations are distinguished into ODEs, which are ordinary differential equations, and PDEs, which are partial differential equations. There's whole classes designed around each one of those. Okay, so we're just talking about differential equations, and of course they're not going to be these kind, they're going to be those kind. Alright, so when you begin with a differential equation like, we use simple example, y prime plus 2y equals 0. That is, first of all, a differential equation because why?
Because there's the
y prime.
There's the y prime.
There's a y prime in it. Does it have to be just a y prime?
No.
It could be like a y double prime. There could be a y prime and a y double prime. There could be a y to the 5th derivative in it, right? That's not 5th power if there's parentheses around it. That's 1, 2, 3, 4, 5 derivatives down the order if you differentiate 5 times, right? So remember, this means something different than this. That means y to the 5th power. Is that a differential equation? No, there's no derivatives in it. That's just a plain old before calculus thing. That is totally, totally different and much more involved. Okay? But we're working with just y prime plus 2y equals 0. So when you're looking at a differential equation like that, you could be doing different things with it, but usually you're searching, trying to find a function a function like y equals f of x, right? Which is a solution to it. Okay? Sometimes you need to know just a specific solution, call those particular solutions. Sometimes you need to know the general solution. Usually any solution method is going to provide you with the general solution. So in this case, for this differential equation, I'm not telling you how I got it, but the general solution is y, there's my function, right? Y equals a constant times e to the negative 2x. That is the function, which is the solution to this differential equation. I didn't show you how I got it, right? We'll see that soon. Mainly today we're just going to be working with how these things relate to each other, okay? You could try to guess. Sure, that's a technique. But a lot of differential equations aren't that simple. This is like the most basic one almost possible, right? We saw some other basic ones yesterday when we were doing slope fields. Most of them you can't guess, unfortunately, but that would work. I mean, you could try. And some of them are guessable. You could guess this one. You guys can figure it out. It would take us a couple tries. But. So in this case, this is the general or the specific solution. What do you guys think?
General.
Since it's got a constant in it. Yeah, any constant. It's the general solution. So these are terms, all this terminology is really important. So that's the general solution because any constant would fit it, right, Dawson? Okay, so something else. So there's like one bullet point. Another bullet point is that each constant, just like Austin said, each constant in the general solution yesterday we saw that there was like a family of curves when we were looking at the slope field, right? We were able to kind of picture the general solution, and we were able to see a lot of it at the same time within the context of the slope field. So I'm going to say family of curves, solution curves. Each one of those constants demands a separate condition. To be narrowed down. The reason I'm writing all this out rather meticulously, monotonously even, is that I think that some of this language really affects how you understand this. And I worked hard to write it out the right way. I think the book does a good job. I don't know if I use their terminology exactly. I don't think so. But I like to think of it like this. So each constant, each one of those C's in the family of curves, it needs a condition in order for you to narrow down that specific constant. What do we call this condition yesterday?
Is it the
The
initial
initial.
condition?
Yeah, so usually, at least in ordinary beginning math, for the ODEs, usually that condition is an initial condition. So that's initial condition, right? The IC. Why is it called initial? Because usually differential equations involve motion, just like derivatives, right? Calculus is everything you learned before in motion. So this initial refers to what? What do you think the word initial means?
Beginning.
It's the beginning. It's like a starting point, exactly. So it's like a starting point in time. It doesn't always have to deal with time, but it's some kind of starting point usually. Remember I was talking about it yesterday, we had the slope fields and I dropped a point in, and that was kind of like the starting point. It didn't really have to do with time, did it? But most of the time, I mean, in a lot of circumstances, it's time oriented. If you're working with PDEs, sometimes the condition takes the form of like an edge. So like you might be working with like a box, for instance, and you're looking at the edges of that box, and where the edges of that box are specify the specific solution. Sometimes the condition is a boundary condition. I don't think we're going to do any of those this year. I may change it up though, so we'll see. As far as I remember, boundary conditions only come up with PDEs. We can't do PDEs. We need Calc 3 for that first. Okay? So once you've used this initial condition, I guess I'll make this briefer. So once you've done this, you've specified the constant that you want that matches your condition, whether it's which one of these, you obtain the, I've been calling it the specific solution, but I shouldn't. You obtain the particular.
So by putting in the IC, is what you're saying?
Yeah. Don't make this hard. I mean, it's just like you start with the general family of solutions, you use some kind of condition, we're going to be using an initial condition, and then you find the specific solution that you're looking for that satisfies it. Okay? Just a lot of language. Okay, maybe we should look at a couple examples. So, let's see, what do we got? So I thought we'd look at these. So maybe y equals sine of x, 2, y equals 4 e to the negative x. We'll start with those. Are those differential equations? No, right? They don't have a derivative in them. Those must be like candidates that I want us to check. So the differential equation that I want us to check is this one. Another pretty simple one. we're not going to be able to solve differential equations that are beyond the most basic ones in this class, okay?
First one's a solution.
Maybe I will show you something beyond the AP. One other technique that's pretty important, which you guys might have trouble with, as factoring it in. You'll like it. Okay?
That was easy.
Yeah. So, anyway, let's just check and see if one of these is a solution. Maybe it is, maybe it's not. Just a guess. This is like what Caitlin said. You guess.
This one's not because it's negative sign minus sign.
Okay, so what's she saying? Did you calculate the second derivative?
I just didn't know what
Yeah, you can do this in your head. First derivative is cosine. Second derivative is negative sine. Do these in your head, right? Some of them simple ones. Negative sine of x is y double prime then, minus y was sine of x. That's negative 2 sine of x. It's supposed to be 0. It's not equal to 0, so is that a solution at all? No. Second one is? See if you can see that. Is the second one? Caitlin says it is. This is so simple you can do in your head, right? So if you have an equation this simple, could you like start guessing around with a little experience? Oh yeah, you could. But if I put like one more thing in there, like y double prime minus 2y prime minus y,
then it's a little bit harder.
I'm guessing becomes harder unless you have a lot of experience. By the time we're done with this chapter, I bet we can figure that out. That's the new thing I'll teach you beyond AP. So this one like cycled back, right? Those e to the x ones, e to the x in differential equations is like the holy grail. It's the key to so much stuff because e to the x cycles. You know what I mean? It cycles. It has a cyclical property in it, just like trigonometry. So when you do this one, you get 4e to the negative x minus itself, and of course that's equal to 0. So that is a solution. Is that a specific, what do I call specific solution?
It's one with an actual
Particular?
form.
Is that a particular solution or a general
No.
solution?
It's a general.
Is it a whole family of solutions or just one?
Just one.
It's just one, right? It doesn't
Yeah,
have
it's
one in
got
it.
So it's particular.
It doesn't have like a constant, a c. It doesn't always have to be called a c, but usually we call it a c, right?
So it's particular.
That's a particular solution. Okay, without me telling you techniques on how to do this at all, can somebody tell me what the general solution to that differential equation is? Just thinking about it, just guessing for a second. You guys heard Caitlin? She's too fast.
Sorry.
What is it?
C e to the negative x.
She said, what if you make the function c e to the
Donna Miller to the
negative x?
administrative office, please. Donna Miller to the administrative office, please.
What she realized is what?
Another.
4 is a constant, so you just
4 is a constant. Does it really matter that that thing was 4? If we'd have done this with anything, if that was 7, or pi, or square root of 2, or 112, no matter what that was, wouldn't the same thing have happened, and we'd have just gotten like square root of 2 minus square root of 2, blah, or 112 minus 112, blah. It would still have worked, so I think that that's the general solution.
What
She
about-
still got it by just guessing, right?
What about c e to the x?
So maybe there's other solutions too. Does c to the x work?
Yes.
would work, yeah, because it will always be,
So this is just
Yes.
one family of solutions. Can you get multiple families of solutions?
yeah.
You can, right? Good comment. I like it. So there's one example. But we're going to call this what again? The
General solution.
general solution. As Todd pointed out, is it all the solutions that possibly exist to
No.
this equation? Well, he just generated a whole other family, right? He said, doesn't that work too? Try it if you don't think so. You take the derivative, you get
Yeah.
y prime is c e to the x, y double prime is c e to the x again. That minus the original in black is still 0. That's a whole other family of solutions. So that could happen too, not very often. That would just be too lucky, too easy. Let's see, what else? So new equation. Look at this one. So, do differential equations have to have like x's and y's separated out? They can have x pieces with trig in them. They can have anything you've possibly ever seen in them, because that's the way that you need to describe the real world sometimes. You know what I mean? It just turns out that there's could be all kinds of crazy things in there. Any of the functions you've seen with x's and y's and derivatives and anything. So that's why there's so much devoted to them. This guy. So I'm going to say someone has handed us the solution. So by some process, someone has handed us a solution that is this. Again, is that general or particular?
General.
It's general, right? Now, they want us to verify it's a solution. So can you verify it's a solution? Number one. Verify it works. Specific solution too. For whatever reason, that's an important starting point. How to write this out is kind of nice. I like to keep things simple, so I go x, y prime minus 3y, that side of the differential equation. And I like to just plug stuff in, so x, y prime is here, minus 3, y is here. And you just simplify down and see if you get it. This is kind of like doing what? This problem right here.
You wouldn't have the 3 in front of the y, right? Would it be 3cx? Oh, sorry, I forgot. Yeah.
See what I'm saying? You got to be careful. This is almost like a let from trig. This is almost like let from trig when we're verifying, and that's what I have to do a lot. This is almost like an identity, isn't it? Yeah. If it's a verification problem, it's like an identity. You're just showing it's true, right? So this one, you got x cubed. You've got 3c and x cubed. There, you've got 3c and x cubed. So indeed, that is 0. Check. It's supposed to be 0. If it's supposed to be 2, it better turn out to be 2 if this is indeed a solution. If you want the initial condition, just plug in. This is like basic algebra, right? Plug this in. So 2 equals c, negative 3 cubed. It's negative 3 cubed.
Oh, wait a second. So
27.
you just listed it in for y?
I just plugged it in. This is like the most basic stuff ever.
So c equals negative 2 comes out.
Yeah. There's nothing mysterious about using an initial condition. It's algebra 1. Okay. The thing I haven't shown you yet is what's our basic technique on how to come up with this, right? I haven't shown you anything with that. There's only one technique on how to come up with this on the AP exam that's tested. I'll probably show you 2 or 3 though. But there's only one that's on the AP, so pretty easy, you know what I mean? Like that's the only thing they can ask you about differential equations. So the particular solution they wanted is what?
Negative 2 over 27.
Yeah, here's the particular solution that they wanted. Okay? So remember, when we're talking slope fields, if we wanted to do the slope field, that matches this differential equation, what would I have to do first? You guys help me? If I wanted the slope field for that differential equation, what would I have to do? Slope fields for all differential equations might be difficult to develop, but for this one I think we can do it. What do I have to solve for if I want the slope field? I need y prime because that's the slope, right? So y prime, if I solve here, is going to be 3y over x. And then we usually think of this as dy dx. That's whose notation?
Leibniz.
That's Leibniz's notation. Why did I switch notations here suddenly? Why do you think I did that?
Because
I'm thinking slope field, and this tells me slope more than y prime does. You know what I mean? This like makes me think slope more. That's why I changed notations there. Right? Yeah, it's like rise over run. Exactly.
so 0, 0 would just be.
So let's put a couple points in here. And let's just see if we can see this cubic family of
Well, it's
curves.
gonna go straight at 0, 0. So that's how it looks. The cube looks that way.
And anything with a y at 0 is going to be straight.
Remember, you might be right, Austin, but all depends on the initial conditions. It's a good hypothesis, though. These ones with x and y's, it's hard to find the pattern, right? So you have to do a lot of them.
There's a lot of diagonal patterns.
There are, right. So usually the ones that involve x and y with your slope fields, they have some kind of pattern along the diagonal. Why? Why is
Because
that?
you have 1, 1, and then 1
Along a diagonal, what's equal to what?
X and
Y is equal to x. That's why you have patterns on diagonals in slope fields that involve both terms. Anyway, though, 0, 0, you plug 0 and 0 in.
You get a 1.
Hmm?
Or does it just
by 0.
You divide by 0, you have an
Straight
indeterminate
up and
form.
down.
Up and down.
I don't know, let's try somewhere
you just
else.
leave it blank.
I think you don't know what that is. You don't even know if it's undefined because it's 0 over 0. It's not 1 over 0, right? Remember when we were in limit land? We'll come back to this at the very end of the year.
0 is 0.
0 over 0 meant, darn, try something else. So let's leave that alone for now. What else have we got though? If we were here,
That is 0 over.
0.
It's something over
No,
0
that's
over
just-
1,
Yeah,
That's
which is
0.
0.
that looks like this.
Same with all the horizontal lines.
So all the horizontals are like that. But then you have your verticals, which are something over 0.
Okay, so this is 1, 1. So this is 3, right? That's pretty extreme. This is 2, 1. So that is,
Where's 2, 1? Sorry.
6.
or 1, 2, I should say, right?
Yeah.
So we get 3 times 2 over 1 is 6.
That's really.
That's even steeper. Is this confirming what you said at the beginning, Austin?
Well, I thought
It's
it
supposed to be like x
this.
cubed, right? So let's see if we get that same kind of thing down here. Let's see if it looks like that pattern. Right here is negative 1, 1. If you put negative 1, 1 in, you get
Negative 3.
Positive.
Positive 3 still, yeah.
3 times negative 1 over negative 1 is still positive 3. That's good. And then down here you're going to get 3 times negative 2 over negative 1 is positive 6, so really steep. Are you guys seeing
Yeah,
that
you can see it.
shape? So it does look like, even though we couldn't do the 0 over 0 thing, from the rest of the family, that's going to be what it looks like. That's what it should look like, right? We just verified that this was what the solutions should look like. Ours came from negative 3, 2, which is 1, 2, 3. I should probably go up more. Negative 3, 2 came from like this dot, landing on this dot. And apparently if you land on that dot, drop your initial condition there, you get this function. Which looks like what? Think about what the transformation looks like. It's negative x cubed, right? So
Would it be
instead of going like this, it should go like this. And the 2/27 should make it thinner, right? Let's see if that looks right. So let's try this one. What does it look there? Negative 3, 2. If we put that in, we get
Negative 9.
3 times 2 over
Halves.
negative 3.
Oh yeah.
So that's like, I think it's going to work.
Yeah.
And then we'd have to sketch out a bunch more of the field to really see where it flows. You guys know what I mean? But I think it's going to look all right. Make sense? Don't make this too hard. I think the concepts in this section are pretty easy. Okay, I think we're good. If you need more examples, let me know.